You're looking at a four-dimensional object. Well, sort of. What you're actually seeing is a 3D shadow of a four-dimensional object, and that shadow's being projected onto your 2D screen. It turns out almost every 3D animation you've ever seen, from video games to Pixar films, models the world mathematically in 4 dimensions. Why? Because it makes the math dramatically easier. In this video, we'll show you how animators model objects in 4 dimensions using something called homogeneous coordinates, and how a clever trick with a 4-dimensional sharing transformation lets us perform 3D translations using only matrix multiplication. The result, faster, cleaner, and more efficient animations. In a previous video, we explained a little bit about the 3D animation pipeline. We showed how to use matrix transformations to move objects from object space to world space. This is where we would scale the object, rotate it, maybe reflect it, and translate it so it fits where we want into our scene. But one of those transformations is not like the other. The translation at the end requires an addition of 2 very large matrices, but the others only require a 3x3 matrix times a large matrix. So 3 by n, where n is the number of vertices on the 3D object. The 3x3 matrices are nice to work with. For example, we can multiply all of our 3x3 matrices together into one 3x3 matrix before multiplying by that large matrix, so we only have to do that large calculation one time. It would be ideal to have all of the transformations as a matrix multiplication, but no 3x3 matrix can represent a translation in 3D space because the origin will always end up at the same place after a 3x3 multiplication. This turns out to be a problem on the next step in the animation pipeline too, changing from world coordinates to camera coordinates. To view the scene of 3-dimensional objects, animators pick a position for the camera and the direction it's facing, and other details like the zoom value of the lens. The coordinates of all the points in the scene need to be changed again so the camera is the origin and the camera axes are the new coordinate axes. This makes it much easier to find out which objects can actually be seen by the camera and which ones are out of view or blocked by other objects. But we have the same translation problem, moving the origin from world space coordinates to the camera space coordinates. That is not a transformation that can be done with a 3x3 matrix and requires a much more computationally intensive matrix addition. This translation problem going from object space to world space or world space to camera space can really slow down computations in the animation pipeline. If only there was a way to translate with matrix multiplication, that would simplify both steps immensely. There is a clever workaround that lets us handle translations using matrix multiplication, but it requires 2 key ideas. First, we model our 3D objects in 4 dimensions using something called homogeneous coordinates. Second, we use a shear transformation to transform the object in 4 dimensions and then look at its shadow in 3 dimensions to see the translation. Okay, that was a lot. Let's walk through the whole process slowly to show how it works. Since we can't represent 4D space well, we'll instead model 2D objects as shadows of 3D objects with the same homogeneous coordinates technique. So here's an example. Suppose I want to translate this card up a couple of centimeters, and the origin is at the lower left corner of the card. I can't translate the card with a matrix transformation because origins remain fixed under those transformations. So what I'm going to do is to move the card up in a different dimension. Now I can do a shear transformation, which angles the stack of cards. A shear is a transformation that shifts squares and rectangles into parallelograms with non-right angles. Notice that with the shear transformation, the origin still hasn't moved, and now the card has moved over the position we want it in. So we can project the card back down to the tabletop and it appears the card was translated. But what was really translated was the shadow or projection of the card. Or seen another way, if we take a bird's eye view, when we shear in 3D, it looks no different to us as if the card was on the tabletop and was translated where we wanted it. A shear in 3D creates a translation of a shadow in 2D. Now let's do the same thing with a computer image. Here's a simplified Millennium Falcon in the XY plane, defined by a list of coordinate points. To fly it around like in the previous video, we can add a vector, like 1, 2 to all the points, shifting it 1 unit in the x direction and 2 in the y direction. But this requires matrix addition, which we'd like to avoid. For speed, we would rather do this with matrix multiplication. So the genius of homogeneous coordinates is to move the object 1 unit above the plane where you want to see the object. This requires using another coordinate for all of our points and adding a dimension to the space we're working with. Changing the old Millennium Falcon coordinates to homogeneous coordinates is easy enough. We add one more row to our object matrix and put a 1 in this entire row. This shifts every point in the Millennium Falcon up out of the xy plane to 1 unit above the xy plane in the z direction. Now the shadow of the Millennium Falcon into the xy plane looks like our original Millennium Falcon. The process of finding the shadow of our object on the xy plane is simple. We just ignore the z coordinates and plot the xy coordinates of our object. Or we could think about zeroing out the z coordinate, and that would drop the object parallel to the z-axis down to the xy plane. Now the next step is to do a shearing transformation in 3 dimensions that shifts the lifted Millennium Falcon in our desired direction. But more on that in a moment. First, let's run through the same process with a 3D object into 4 dimensions. Here's a list of points for a 3D object. Now we want to shift this entire object up 1 unit above this 3-dimensional space that it is in right now. We can't show you what this looks like, but we know how to do this mathematically by doing the same strategy we just used. We add another dimension into our object matrix, we could call it the w-axis, and we populate the new coordinates with 1s for every point. Now these coordinates represent this 3D object 1 unit above the 3D space, whatever that means in 4 dimensions. Okay, now let's go back to our 2D Millennium Falcon that is 1 unit above our plane. If we move our Millennium Falcon that is 1 unit above the xy plane, then the shadow will also move and will be a translation. But how can we move the upper Millennium Falcon with a matrix multiplication if we couldn't move the original in the xy plane? Well, the answer is with the shear transformation we mentioned earlier. A shear parallel to the x direction slides all lines parallel to the x-axis with the amount of slide proportional to the y-coordinate. In 2 dimensions, a shear matrix parallel in the x direction has this form. This number in the upper right position, it has a nice interpretation. This is how far to the right or left the line 1 unit above the x-axis gets shifted. If we put a 2 here, this line gets slid to the right 2 units. If we put a -3 here, then the same line gets shifted to the left by 3 units. This form extends to 3 dimensions. This matrix shifts the plane 1 unit above the xy plane, a units in the x directions, and b units in the y direction. Notice the origin of the 3D space still stays in the same place, but the plane 1 unit above the xy plane does get shifted, and if we take the shadow of our object down to the xy plane, then it looks like we just translated the object. Not only that, we translated it by the vector AB, where a and b are the x and y coordinates of the translation vector. That is why translation matrices in 3-dimensional homogeneous coordinates often use t sub x and t sub y instead of a and b to represent the translation in the x and y directions. We can now extend this to 3-dimensional shadows of 4-dimensional objects. The translation matrix can be written this way, where the top 3 values in the right-hand column are the values to translate the objects in the x, y, and z directions, respectively. Now, if we take an arbitrary point in homogeneous coordinates, we can see algebraically that the x, y, and z coordinates get the correct values added to each one for the translation. Multiplying the translation matrix by an entire matrix of object points is the same as adding a large matrix of shifts to the x, y, and z coordinates. Okay, so let's go back to the beginning. Why did we want to avoid this addition if multiplying by this translation matrix does the same thing? Because now we can take all of the transformation matrices needed to change the coordinates from object space to the world space. Those could be scaling matrices, rotation matrices, reflection matrices, and translation, and multiply them all together and do all of those in just one matrix. Not only that, but the next step in the pipeline, to move to camera coordinates, can be done with another 4x4 matrix that can be multiplied together. So in the end, there's only one 4x4 multiplication times the large object matrix. That's very slick and much easier than some matrix multiplications, then additions, then multiplications, then additions. Since homogeneous coordinates are used so extensively in animations, you may think that they are a relatively new invention, but they were actually developed almost 200 years ago by August Ferdinand Mobius, the mathematician famous for exploring the Mobius strip, a surface with only one side and one edge. So I think it would be appropriate to end this video with an animated Mobius strip that uses 4-dimensional homogeneous coordinates to create the animation. Thank you for watching. Please subscribe and share our videos. Be sure to follow Math the World on Twitter, Instagram, and Facebook. Thank you so much for your support.